Is light made? Light is made by electrons. So electrons in the atoms themselves of gases make light. And those electrons can do things. They can jump up when they absorb light, or they can jump down and release light. So it depends on how far that electron falls for how much energy is released. Here we have a regular electron. It's not doing anything. It's got a nucleus. It's got electron shells, but there's no electrons yet, just so you can see what an atom looks like. These rings outside the nucleus represent electron shells or electron orbits where electrons can be. Now, obviously, this is a simplified diagram. This isn't actually what it would look like in real life, but it's great for learning purposes. Okay, let's add in electron. So now we have an electron in that shell. Now the electron cannot be between the shells. It doesn't want to be there. It can't be in this area between here. It can't be in the area between there. There could be more shells outside here, but for now, let's just focus on these three. Electrons can only be in these orbital shells, okay? Now, one other thing before we move on is electrons really, really, really want to be close to the nucleus, but not that close. Electrons are negative. Nucleuses are mostly positive, and so positive and negative attract, and they want to be close. So if you were to pull this electron away, it would want to get right back to the positive center again. And that's why most electrons will fill in the inner shells before they fill in the outer shells. Well, here's the thing. You can give these electrons pushes. You can push them away from the nucleus. And if that happens, the electron moves to a different shell farther out. So in this case, the electron jumped from the first shell to the third shell. Now, it could have jumped to the second shell. It just depends on how much energy it absorbs, and that depends on where it goes upwards. If it absorbs enough energy, it can jump up 2 shells. If it doesn't absorb enough energy, it could jump up no shells. That's a possibility as well. The energy could pass right through the electron and do nothing to it. So it takes energy to move electrons. So when you guys said heat, when you said electricity, yep, that's the energy it takes to move an electron. Electricity can move the electron from here to here. Heat can move it from here to here. So that's what we get to move electrons up. Now, no light has been released yet. So what's going on? Well, that electron doesn't want to be up there. It wants to fall back down. It has potential energy. Just like an object that's high up in the air can fall back down, electrons can fall back down. And so it jumps to a lower orbit, and jumping back down releases light. So we finally have our light. In this case, yellow light is released. And that yellow light can go flying off, that photon can go flying off into whatever direction it wants. So the more it jumps down, the more energy it released. So it could have jumped down twice, once the middle shell and once the lower shell, and it would have released 2 photons, but those photons would have been of lower energy than jumping down once jumping down one time to a much lower shell. So the farther the jump, the higher the energy light that is released. Now, each atom is different. No 2 atoms are the same. So each atom has a different number of electrons. Each atom has a different number of electron shells. Those electrons can be filled in a shell. There could be empty shells. So it just depends. And each atom, because it has different electrons and different electron shells and different fills, means that each atom will absorb completely different wavelengths of light, and each atom will release completely different wavelengths of light. You can have an atom here that releases 2 types of blue light and 1 type of violet light. You could have an atom down here that releases an orange, a yellow, and a red type of light. So just know that all atoms are different. No atom will release the same wavelength, or I should say no element will release the same wavelength of light as any other element. So just keep that in mind. They release different types of light, very distinct wavelengths. And we can actually use that to tell what something is made out of based on the light it emits. Always good to know, the shorter the wavelength of light, the higher the energy. So for example, violet has a shorter wavelength than red. So violet is higher energy light than red, just so you know. Okay, so let's say you have an atom, and that atom is sitting around, but it's not in the state it wants to be. Its electrons, as you'll notice, are in higher shells. They don't want to be up here. The electrons want to be close to the nucleus as possible. So something has pushed these electrons out. It could be heat, it could be electricity, who knows? So these electrons are far out and they want to fall back down, and so they do. And so the electrons fall back down into lower shells. Some of them drop to the lowest shell, some just drop a little bit. And as they drop, each one releases a photon of light corresponding to how much energy it had. So how much potential energy was stored here that is released as light here. So this one only dropped a little bit, so it released low energy red light. This one dropped 3 shells, so it releases high energy purple light. And everything else in between, 2 yellows and a blue. So when an electron falls, light is released. Okay? Based on the size of the jump tells you how high energy that light is. So that would be an emission spectra right here. And these lines right here correspond to the light that was released by those electrons. So each one of these lines could be a single electron, or it could be an electron that jumped down twice. Like maybe these 2 reds are 1 electron that falls down 2 shells separately. Or it could just be 1 electron for each line. It just depends on the atom. But yeah, emission spectrum, when an atom releases light, its emission spectrum is the type of light that is released for that particular atom. So maybe this atom is neon. Who knows? Maybe this atom is argon. Probably not argon, actually, but you get the idea. This is a particular atom, and it releases just these wavelengths. It'll never release any other type of light. Never. So if you have one element, it'll only release this type of light. I should call them tubes, actually. So yeah, neon lights are just emission spectrum. That's it. Just specific elements inside a tube of whatever that element is. Electricity heats those electrons up, pushes them out, and then they fall back down and again and emit light. So that's how neon lights work. Actually, that's how a couple different lights work. Same thing for compact fluorescent lights. And LED lights, it's something similar as well. LED lights are an emission spectrum too. But here you go. If you learn nothing else today, you learn that all neon lights are not actually neon, just the red ones. Okay, now let's talk about absorption spectra. So absorption spectra, let's say you have an atom. It's a gas, right? It's got on its electrons, so it's not a plasma. And those electrons are hanging out mostly in the lower orbits. I don't know what this one is doing. It should be down here. But most of them are in their lowest energy state. They're as close to the nucleus as possible. They really don't want to go anywhere. Well, too bad. So light comes in, it hits those electrons, and you'll notice that a lot of those electrons are pushed to a higher orbit. So if you were to shine a light with all colors, the entire rainbow, through a gas, some of those photons will be used to jump those electrons out to a higher orbit. Now you'll notice that other photons, like this blue, green, and tan, other photons are actually not absorbed and just go right through the gas, like it wasn't even there. So you could think of this almost like, air. Well, although air would actually do the opposite. Almost think of like this gas as air. And as the sunlight goes through that gas, some of those wavelengths are actually absorbed by the gas, whereas some can go through and we can see them with our eyes. So that would kind of be like an absorption spectra. Some wavelengths are absorbed. Now you'll notice that now that these electrons are pushed out to their outer shells, they're going to want to fall back down again. And yes, they will. So here's what an absorption spectra would look like. It's the entire wavelength of colors, the entire rainbow, but some wavelengths are missing. And these black spots correspond exactly to the wavelengths that are absorbed by these electrons in that atom. So the electrons that were absorbed are obviously not permitted through the gas, and so they're missing. And that's what we get with an absorption spectra. So a rainbow that's missing some colors. Now, you may notice something here. Those lines match perfectly with the lines from the emission spectra. So an atom's emission spectra will match up almost perfectly with his absorption spectra, which makes it nice because you can just look at your emission spectra here on Earth, and then you could look at a different distant star and say, hey, wait a second, those emission spectra lines match up perfectly with the gas in the star. It must contain neon. And actually, yeah, that will work most of the time. So there's absorption spectra and there's emission spectra below it, so you can compare. Okay, now let's get to our next topic, which is black bodies. So where are we getting the rainbow light from? The rainbow light comes from black body sources. So a black body is any high temperature object. That's literally it. Any high temperature object will be a black body emission. That means it's heating up those atoms and emitting all the wavelength of light. This could be a light bulb, like you see in this picture here. Now, hold on. When I say light bulb, it could be an incandescent light bulb. It has to be one with the filaments that heat up really, really hot. So Christmas lights, incandescent lights, spotlights, any of those higher power lights will be incandescent. LEDs, fluorescents do not count. They are not continuous spectrum. They are more like emission spectrum than continuous. Stars. The stars themselves, if they had no atmosphere, would be a great continuous spectrum source. They're really hot, right? High temperature, stars are hot. Fire. Fire is pretty good at this too. So if we were in person, we would be looking at a candle, and a candle actually emits every wavelength of light. Hot objects, like if you have a hot piece of metal, yep. Even though hot pieces of metal usually emit higher red, they do emit every wavelength of light. So think of, for a black body, anything that's really, really hot. Done. Okay, now let's put it all together. Let's say you're an astronomer and you want to know, I want to know what this atmosphere of this star is made out of. What is the gases hanging out around this star? So imagine the light bulb is a star. You point your telescope not at the star, but at the gases hanging outside it, maybe the corona of our sun. Yeah. So you point it at the corona or the chromosphere of our sun. You're like, I want to figure out what the chromosphere of our sun is made out of. And what you get is you get these lines, these emission spectra from the gases that are heated up by the star. They emit their wavelengths, and you can pick them up with your spectroscope. And so it actually would tell you what elements our star's corona is made out of. And believe it or not, this is actually how helium was discovered. Helium was discovered with the emission lines from our sun itself, because helium itself is pretty hard to single out here on Earth. So astronomers actually discovered helium's lines before we knew about helium on Earth, crazily enough. Now, let's say you wanted to figure out, okay, I want to know what the photosphere of the sun is made out of. What are the gases in the photosphere? Well, you point your light directly at the sun, and what gets absorbed is the gases between the sun and you. So it could be, the photosphere of the sun, the chromosphere, the corona, even Earth's atmosphere will actually absorb some of these gases as well. So what you get is an absorption spectra. All the elements that are between you and the star, they block specific wavelengths, and those show up as black lines. So you can tell what is between you and a star by what these black lines block. And actually, this is how we know what's a nebula. So